Welcome back to the next video in the IB Math A higher level topic subsection explanations. So today we'll be looking at differentiation. So basically differentiation is finding the rate of instantaneous change. You probably know about gradients, so a straight line has a gradient, which is the rate of change of that straight line, so the rise over the run. The differentiation is the process of finding the exact same thing but for a curve. So basically, as you can see here, we have a cubic graph, and if we just pick a random 2 points, we can find a straight line going through them, and then finding delta y by delta x just gives us an approximation of the rate of change. But if we want to find it only at a certain point, then we'd have to create a tangent. That means a line going only through that curve. And differentiation is basically how we do that. So this formula right here, f of a plus h minus f of a divided by h, is literally the exact same principle as a gradient. So if we pick any arbitrarily small h, so say 0.00001, and then find f of a plus 0.0001 minus f of a, divided by 0.0001, we're going to find the rate of change at an arbitrarily small value. So that's almost the exact rate of change. But if we were able to find the limit as that h approaches 0, that means we have almost nothing there. That is our derivative, the instantaneous rate of change. So more formally, this is how we write it. So the derivative is called f prime of x. That's what this apostrophe here is. And f prime of x is just the limit as delta x approaches 0. That means the change in x, so here I've written it as delta x. Here in this example it was given as h, it's your choice. So you could say h approaches 0. So the limit as delta x approaches 0 of f of x plus delta x minus f of x, all divided by delta x. So if you think about it, this is just the change in y by the change in x. But here y is this entire quantity here, and x is just delta x. So yeah, that's pretty much the entire thing of differentiation. So as delta x approaches 0, this gets infinitesimally smaller, this gets infinitesimally smaller, so we approach the actual derivative very closely. So here's sort of a derivation of how we take it from this to the actual derivative operator. So let's just say we're working with the function x squared. Now we'll learn later on that the derivative of x squared is just 2x, but keep that in mind for now, and I'll take you through the steps initially how we do it here. I'll go to the next slide later, and then I'll come back to this. So with the formula we just learned, limit of h approaches 0 of f of x plus h minus f of x all by h, we can substitute x squared in. So here it would becomes x plus h squared, because this entire thing is treated as x, minus x squared divided by h. And then here we just expand this x plus h squared out. So what this gives us is basically a quadratic equation, x squared plus 2xh plus h squared minus x squared. And then what I do here is I just cancel off these x squares, because we have a plus x squared here, a minus x squared here. So we have 2xh plus h squared divided by h. If we divide out the h now, because we have a h here and a h here, we get 2x plus h. And if we just substitute h equals 0 in, we get that it's actually equal to 0. Equal to 2x. So the derivative as h approaches 0 is 2x. And let's just quickly look at the power rule. So this says that if we have x to the power of something, so any number, x to the 7, x to the 69, x to the 67, x to the 42, x to the whatever, 542, I don't really know, whatever. So we just have to bring down that number and take away 1 from the power. So if we have x to the 67, for example, that would be 67x to the 67 minus 1, which is 67x to the 66. If we have x squared like we did earlier, we bring down the 2, so that's 2x to the power of 2 minus 1, which is 2x to the 1, which is the same as 2x. That's why we got 2x here using the limit approach as well. So here are a list of common derivatives. Now, because you can't really apply this sort of rule to things like sine, cos, tan, log, ln, all of those things, you just need to memorize some of these. The key ones to memorize here are a to the x, because that just means the base is a constant and the exponent is a variable. That's something like 2 to the x, which in this case would be ln 2 of 2 to the x for the derivative. And keep in mind here, the base has to be greater than 0. And then here, the derivative of e to the x is the exact same. It's e to the x. The derivative of log base a of x is equal to 1 over x natural logarithm of a. The derivative of the natural logarithm is 1 over x, and this can be derived by using number 4, so I encourage you to try that. The derivative of sine x is cos x, of cos x is negative sine x, of a tangent x, I don't know why it's written like this, it's tan x, but the derivative of tan x is 1 over cos square x, which you can also write in a very, very much more readable manner, because if you know that cos is 1 over cos is actually a secant of x, you can write that as a sec square x. And then here we have cot x, so that's negative 1 over sine square. We have arc sine, which is 1 over square root of 1 minus x square. We have arc cos, which is negative 1 over square root of 1 minus x square. We have arc tan, which is 1 over 1 plus x square. And then arc cot, which is just the same as arc tan, but with a negative in front. The square root of x can be derived using the power rule, so again, I encourage you to try that. This can also be derived using the power rule, and this can also be derived using the power rule. So it's a good sort of exercise. But I suggest you memorize all of these from 2 to 13 because they can be very useful. So now there's a couple more rules to know. The first one of these is called the chain rule, and that's when you're differentiating composite functions. So for example, if you have 2x to the cos x, then you have a composite function, because the base function is just x, and then the composite is the base function, the inner function here is a cos x, and then the outer function is x to the something, right? So x to the x. So our function is actually two separate things. So what you'd do here is you'd initially differentiate x to the cos x with respect to cos x. So that means you follow this rule over here. And then you differentiate the inner function, which is cos x, which gives you sine x, negative sine x, sorry, and multiply that with the result of this. So that's basically the chain rule. It's used when there's a composite function, so when you're finding the derivative of f of g of x, you know that the derivative is actually equal to the derivative of the inner function times the derivative of the outer function with respect to the inner function. Now, rule number 2 is the product rule. It just means that when you're derivating a product, so f of x times g of x, so say I'm differentiating 2x times cos x, then I first find the derivative of cos x and multiply that by 2x, and then add that to the derivative of 2x multiplied by cos x. So if I did that example, 2x cos x, I know that the derivative of cos x is negative sine x, so this would be negative sine x times 2x, so that's a negative 2x sine x, plus cos x times 2, because the derivative of 2x is actually equal to 2. So that's the answer here. And then this third one is the quotient rule. I suggest you don't use this, but in case you do want to, it's just that if we have f of x divided by g of x, it's the exact same as the product rule, except we had a subtraction here, and then we square the denominator. So now let's look at points of inflection. So this basically means when the derivative of the derivative is equal to 0, we have a point of inflection. That might sound a bit tricky, but I'll tell you what that is. So if we go back up here, we know the derivative of x squared is 2x. So if we just differentiate this again, we get 2. And so the second derivative of x squared, the derivative of x squared, is just 2. So here, for instance, if we had the graph of x squared, the second derivative is 2, and 2 never equals to 0, so we don't have a point of inflection there. But if we had x cubed, for instance, then we would have 3x is the point of inflection. So when 3x equals 0, then then we have a point of inflection. And what a point of inflection actually is when the sign of the function changes. So as you can see here, it's going up, and here the rate of change goes from negative to positive. And so it sort of just changes here, and now we have an increasing function. So this point right here is the point when the sign, or the concavity of what we call it, the concavity of the function switches. So now let's try a question. We've basically completed the entirety of differentiation except for one part, which is called related rates of change. Now, this is just an application of everything that we've done so far, and I think the best way to tackle it is with an exam-style question. So please take a go at this question, and I'll give you the solutions for this in a couple moments. Alright, so now that you've hopefully done the question, here are the solutions. So first, we know here that volume is 5 pi h squared minus 1/3 pi h squared. So what we're going to have to do to find the rate of change of liquid is take the derivative of this, which is dv by dh. So that's what we're going to try and find. So if we differentiate this, we get 10 pi h, because we bring the 2 down and we subtract 1, minus pi h squared, because we bring the 3 down, which gives us 1 over 3 times 3, which is 1, and then h to the 3 minus 1, which is 2, so this is this. And then we multiply it by dh by dt. What this means is we're taking the derivative with respect to t, but we don't have any t here. So we just write times dh by dt and rearrange for that later on. So next what we do is we just sort of rearrange, like I said. We plug in our values here, so into this equation to find v, and then we find a value of h. Now that we have a value of h separately, we just plug that value of h into this first equation, and then we rearrange for dh by dt, which gives us that dh by dt is 0.0261 centimeters per second. And with that, we've completed the entirety of differentiation that you need to get a 7 in Math AA higher level. I hope that you found this video helpful to watch, and please do let me know down below in the comments if you have any questions or require any clarification regarding anything. Thanks for watching.